So I'll be talking about connecting Perebor conjectures towards a search to decision reduction for minimizing formulas. And so the first part of this title is connecting Perebor conjectures. And so what are the Perebor conjectures? In the 1950s, mathematicians in Russia were really interested in the following question. What computational problems require Perebor, which roughly translates to brute force search? So like what algorithmic questions do you have like no hope of avoiding just the brute force search algorithm for? And so there's an excellent history of this research program written by Trachtenbrot. And two problems that he mentions in his history are called task 1 existential and task 1 constructive. And so in task 1 existential, you're given some function and you want to determine if it has circuits of a given size. And in task 1 constructive, on the other hand, you're given a function and now you want to actually find the smallest circuit. Instead of just determining it, you want to actually output it. And so in modern parlance, this first problem is called MCSP and the second problem is called search MCSP, and I'm going to define them more formally on the next slide. But hopefully this gives you a gist. And both of these problems, the existential and the constructive version, were conjectured to require Perebor. And so one thing that's kind of interesting is that morally it feels like the Perebor conjectures for these two problems should be equivalent, but only the trivial direction is really known. Obviously, if you have some algorithm that beats brute force for the constructive version, you get an algorithm for the existential version, but the reverse direction is not known. And so in this work, kind of like the one-sentence summary is that we show that there is some non-trivial connection if you replace circuits by formulas. So let me now define MCSP a little bit more rigorously. So MCSP stands for the minimum circuit size problem. And this problem is going to take two inputs. The first is the truth table of a Boolean function. And so that's just the list of values the function takes on all of its inputs. And this is represented as, can represent this as a string. And the next thing is some size threshold. And the output of MCSP is whether or not there exists a circuit of size with at most S wires computing F. And so there's kind of two notes I want to make about this definition. The first is that in order for this to be really precise, I should really say exactly what my model of formulas is, but I'm just going to omit that for now and come back to it later. And the other thing is a notational point. Kind of looking at this problem, there are two quantities that you kind of want to denote by n. The first is the number of inputs to this function f, and the second is like the length of this string, the length of the truth table. And so the convention that we're going to adopt is that little n is going to denote the number of inputs to the function, and capital N is going to denote the length of the truth table, which is exponential in the number of inputs. So that's the decision version of MCSP. You can also consider the search version, which, given some truth table T, now actually output a minimum size circuit for F. And so that's the decision in the search versions of the problem. And so the rest of this talk is kind of inspired by trying to understand MCSP and the complexity of MCSP more. But the viewer, maybe you're wondering, like, why should we care about MCSP at all? And I won't have too much time to get into this, but maybe I'll say a little bit briefly about it. The reason I think it's so interesting is the connections the problem has. It has these kind of really cool connections to cryptography and learning theory, and also to other parts of complexity theory, like average case complexity and circuit complexity. And so while I don't have so much time to talk about this now, if you're interested in learning more about it, I gave a talk a couple of weeks ago that's available on YouTube, in which I spend like a couple minutes describing the connections to each of these things. And so if you're interested in learning more about MCSP and what these connections are, you feel free to check it out. Okay, so what do we know about the complexity of MCSP? And for pretty much everything I'm going to talk about on this slide, or the things that I'm going to talk about on the slide were noticed in this paper by Cabinets and Tsai in 2000, which was kind of like a foundational paper, and it began kind of like the modern era of researching MCSP. And so they were considering the complexity of MCSP, and first thing to realize essentially by definition is that MCSP is an NP. If you want to witness that a function has a circuit of size at most s, you can just hand over that circuit, and then the other person can check whether or not it computes the function. So it's an NP. Could it be in P? Probably not. So Cabinets and Tsai realized that if it were in P, then you could break crypto. Like one-way functions wouldn't exist, PRGs wouldn't exist, all that good stuff that we like wouldn't exist if MCSP was in P. So it's probably not there. And so then the natural question is, is it NP complete? And this is a big open question even today. We still don't know what the answer is, but what Cabinets and Tsai showed is that giving a positive answer to this would require a breakthrough. So like there's some formal sense in which showing MCSP is NP complete requires showing breakthrough circuit lower bounds. And so that's kind of like a barrier to proving NP completeness. I just want to emphasize that we believe this consequence. We believe that these circuit lower bounds hold. So this is an evidence that it shouldn't be NP complete. We just, don't know how to prove them. So it's kind of like a technical barrier to showing it's NP complete. And so we can't show a straight up NP completeness result, but like you might want to look at the problem a little bit more. Does it have the properties required of NP complete problems and stuff like that? And Cabinets and Tsai noticed, well, on the one hand, all NP complete problems have a search to decision reduction. And this basically follows from the fact that SAT has one and the definition of NP completeness. But on the other hand, it's not clear whether or not MCSP should have a search to decision reduction. And this is exactly the question whether or not the existential version of task 1 and the constructive version of task 1 are equivalent. And so if you believe MCSP is NP complete, then you have to believe it has a search to decision reduction. And so the fact that we don't know one for MCSP yet, is I think an interesting open question. Now, while we don't have a full search to decision reduction for MCSP yet, we do have these kind of like almost search to decision reductions. And there's a bunch of different works which use or make one of these. Like we have search to decision reductions that output like approximately optimal circuits, or they output a circuit for most inputs for a slight variant of MCSP, so it's like an average case version of a search to decision reduction. But what I think is most interesting about these like partial results is that they seem to be like kind of important ingredients. So there are these results that I think are really cool that use search to decision reductions, or like maybe I guess it depends on your perspective whether or not they're an ingredient or a byproduct. So there's like this result by Carmesino and Pagliazzo, Cabinets and Kolokova, which gave like these new learning algorithms through connections to natural proofs. And kind of as a result of their techniques, they prove a search decision reduction, an approximate search decision reduction for MCSP. And then there's also a result by Hirahara, which gave this kind of amazing possible non-black box worst case to average case reduction for NP. And there he like really crucially uses this search to decision reduction for MCSP. So for me, kind of philosophically, like looking at this from like 100-foot distance, like maybe understanding search to decision reductions for MCSP could be something fruitful and could lead to some interesting things in complexity theory. And while we have these partial search to decision reductions, like the original question of exact worst case search to decision reduction is still open. So now I want to talk a little bit about our results. So in one sentence, our results are better than brute force search to decision reductions for the formula version of MCSP. So there's a bunch of things to unpack here. What do I mean by better than brute force? What do I mean by formula version of MCSP? I'm going to start with the latter. So the minimum formula size problem, or MFSP, is defined as follows. It's going to take the same inputs as MCSP, the truth table of a Boolean function and some size threshold, and it's going to output, does there exist a formula with at most S leaves computing F? So this is like the size of a formula, the number of leaves it has in its underlying binary tree. And here I just want to be a little specific about what I mean by formulas. So the model of formulas is not so crucial for our result, but just for concreteness, we'll say, it has, you're allowed to use and or gates of Fanon 2, and there's not gates are all pushed to the bottom. All the results will also work for like the B2 basis, if you know what that means. And yeah. So now let me just state these results more explicitly. So our results is that if you got an Oracle access to the decision version of MFSP, then you can solve the search version in the following time. So for the first line, I just included the brute force algorithm for context. So by just using brute force to find an optimal circuit for the function, you can solve the problem in time 2 to the capital N, essentially. And our main theorem is that you can actually solve search MFSP using an Oracle to the decision problem in time polynomial in the input length times this quantity, the number of near optimal formulas for F. And I'm going to define this explicitly on the next slide, but roughly it just means the number of formulas that compute F that are within an additive n+1 of being optimal. But I'm going to be more explicit about this on the next slide. Now, this is cool that we can do it in this much time, but unfortunately we don't understand this quantity very well. We don't really know very much about the number of near optimal formulas a function should have. Even so, we're able to get some interesting consequences that are able to beat with the brute force algorithm. In particular, in the average case, we show that there's a 2 to the order n over log n time algorithm that works for all but a little of one fraction of inputs for solving search MFSP. And in the worst case, you can actually beat this 2 to the n time algorithm by a constant in the exponent. So now you can get a 2 to the 0.67 n time algorithm, although here we have to use randomness. So my informal takeaway of these results is the following. Because we're beating brute force here and we're beating brute force there, you're actually able to show that in some sense, the Perebor conjecture for search MFSP is indeed equivalent to the Perebor conjecture for MFSP. So this is showing that like task 1 existential for MFSP and task 1 existential for the formula version, or constructed for the formula version, are indeed equivalent. So what exactly do I mean by near optimal formula? Let me define this precisely. So just repeating the theorem statement here, we're saying that with Oracle access to the decision version, you can solve the search version in time poly n times the number of near optimal formulas. So just some notation here. I'm going to let L of F denote the minimum size of a formula computing F. And now I can define what I mean by near optimal. So we say a formula phi is a near optimal formula for computing F if it computes F and if it's within an n+1 additive term of the optimal complexity for F. So this is like the size of the formula, which is just the number of leaves in the underlying binary tree. And we're asking if it's an additive n+1 away. And before I get to that, and so like the problem with this result is that like we don't really understand this quantity very well, so it's hard to like convert this into a useful algorithm unconditionally. what we do know is like sort of like average case bounds on this. In fact, if you like take the Lyapunov upper bound for the maximum formula complexity of a function on n bits, and in fact, we are going to use a subsequent improvement by Lodgkin, and you plug that in, you get that with high probability, a random function is going to have at most this many near optimal formulas. And if you combine this with our theorem, we get the average case result that I was talking about earlier, that there is an algorithm solving the search version with an oracle to decision version that runs in time 2 to the O of n over log n for most functions. And that's how we get our average case algorithm from our main result. And I should say that like while while this bound is already good enough for us to beat brute force search, I hardly think it's optimal. In fact, if we were talking about Kolmogorov complexity instead of formula complexity, the analogous bound you'd get here is that there's, with high probability, a random function has polynomially many near optimal descriptions. And really the barrier in pushing this bound down is getting tighter upper bounds on maximum formula complexity. So I think this should be able to be improved, but yeah, I don't know how to do it. So that was our results. Now I want to kind of talk about how we prove those results and what techniques we use. And our approach for solving this problem, for solving search MFSP, works in a top-down way. And what do I mean by that? Well, what we're going to do is we're going to build a formula for computing f as follows. We're going to start with the function f, and we're going to find new functions g and h that are going to be like feeding into a top gate. Feed into the top gate of our formula for f. So we're going to start with f. We're going to find functions g and h that kind of optimally decompose f, and we find a gate that is useful there too. And then what we're going to do is recurse. So we start with f, find a good g and h, then recurse. Now, looking at g, find a way to decompose it, and so on and so forth until we get down to functions that are computed by the input bits, and then we're just done. We let it be computed by that input bit. And so that's going to be kind of our approach working top down. And so one can formalize this as follows. I'm going to let diamond denote kind of like an arbitrary gate. And we can say that G diamond H is an optimal decomposition of F if both of the following hold. One, this decomposition actually computes F. And two, you can obtain an optimal formula for F by taking an optimal formula in G for G and plugging in here, an optimal formula for H and plugging it in here. And so note that there shouldn't be a +1 here. You actually get equality because we're talking about leaves in the binary tree. So you actually achieve the equality here. So that's an optimal decomposition. And that lets us define, the decomposition problem, which says, given some function f with that requires non-trivial formulas, output some optimal decomposition of f. And this algorithm that I talked about earlier on the top of the slide, where you work top down, is precisely showing that if you had an algorithm for solving the decomposition problem, that implies you have an algorithm for search MFSP. So in the remainder of the talk, I'm going to be talking about how to solve the decomposition problem. So just to review, there's this definition of optimal decomposition, which says you can compute the function via this decomposition, and the complexity of the function, you can actually achieve a formula for computing this decomposition that is optimal. So now let me talk about what the pseudocode for this reduction looks like. And so what we need to do in this reduction is take as input some function f, which has non-trivial formula complexity, and we want to output some optimal decomposition of f using our oracle to the decision version of MFSP. And just as a reminder of what optimal decomposition is, I've put the definition here. So the first piece of our algorithm, and really the crucial piece of our algorithm, is some sort of heuristic. And what we want this heuristic to do is going to be a heuristic that's like specialized to f, and we want it to accept strings of the following form. We want to accept all strings that are a prefix of a function in an optimal decomposition of f. So that was kind of a mouthful, so let me unpack it. So what do I mean by a function in an optimal decomposition of f? I mean, there is some decomposition of f such that this function is either g or h. It's like one of those two. So that's a function in an optimal decomposition of f. And I'm going to say s is a prefix of that function if it's like this string is a prefix of that function's truth table. So like the prefix of length 1 would be like just the value of the function on its lexicographically first input, and so on. So that's a prefix of a function in optimal decomposition of f. And so I'm not going to explain too much about how this works and how we get it on this slide. I'm going to concentrate on that in the next slide. But for now, you can just view this as some sort of black box. We have some heuristic that all prefixes of functions in optimal decomposition of f pass. In fact, there's like a trivial instantiation of this heuristic where you just accept every string. We'll have to do something a little bit more clever to get an efficient algorithm. But for now, just think of this as some black box. So we have some heuristic that does this. And now if we have this heuristic, in our next step, we generate a list. In fact, we generate a list of all total functions that pass the heuristic. And we note that like we can actually do this efficiently because of like this prefix property. Indeed, what we can start is we can start with an empty prefix, and then we can just like add one bit to it, see whether or not that passes the heuristic. If so, we extend the prefix, and then we like keep going. That way we can like find all the total functions that pass the heuristic by extending the empty prefix kind of bit by bit and seeing if it still passes the heuristic. So that's the second step, listing. And we can do this efficiently as long as we have an oracle to the heuristic. And the heuristic like doesn't accept too many things. And finally, once we had this list, we can actually find an optimal decomposition by just looking over all pairs of functions in this list, looking over all possible gates, and checking whether or not that is an optimal decomposition. And note that we can actually do this check because we have an oracle to MFSP. And so we can actually check the second condition here. And the other thing to note is just because the heuristic actually does accept functions in an optimal decomposition of f, you're actually going to be able to find one in this find step. So kind of in summary, this gives a good algorithm if you have the following two properties holding about the heuristic. The heuristic runs fast for like this like prefix extending thing, and also the heuristic is a good filter so that like this list L is not too long, and like the prefix extension thing doesn't take too long to find the total functions. So yeah, so that's the pseudocode for how this works, and kind of the intuition that you should have at this point is that it should yield a good algorithm if you had a fast heuristic that's a good filter. So now let me talk a little bit about this heuristic. The goal of our heuristic is like kind of decide whether the input string is likely to be a prefix in an optimal decomposition of f. And you know, for this talk, because of time constraints, and just to give you the intuition, let's forget about the free prefix part. Let's just assume you get some function f that you want to decompose, and you get some function g, and you want to decide whether that full function is likely to be in an optimal decomposition of f. And so kind of like this baby heuristic can be formed as follows. So I'm going to define this new function, which I'll call select fg, which takes n+1 bits as input. And it's going to act as follows. It's basically going to take this extra bit as input, and if that bit is 1, it outputs f, and if that bit is 0, it outputs g. So in some sense, this is like the concatenation of the truth tables F and G, if that means anything. And then we can define our baby heuristic as follows. Some function G passes the heuristic if the complexity of the select function is just one leaf more than the complexity of F. And so that's defining our heuristic. And kind of the two properties we want our heuristic to have is that it's valid, that all functions in an optimal decomposition pass this heuristic, and that it's useful, that not too many other things pass this heuristic. And so now I'm just going to outline the intuition for like why this heuristic has both of these properties. So with regards to validity, suppose G and H are in an optimal, form an optimal decomposition of F, in particular if G or H forms an optimal decomposition of F. What does that mean? Well, it implies that there's some circuit or formula of size L of F that looks like this at the top, which computes F. And now I want to argue that there must be a formula for the select function, which has only one more leaf. And in particular, you can achieve that, in this case with an OR gate on top, by doing the following. By adding one AND gate over the G, or over the H function, and putting that to the Y input. And so why does this work? Well, if Y is equal to 1, then the input here is 1. So this AND gate is just going to output what was on the other input. It's just going to output H, in which case this old formula is now going to still work in the same way. So it's still going to compute F. So if Y is equal to 1, then this formula still computes F, same as this. On the other hand, if Y is equal to 0, then it's going to the output of this wire is always going to be 0, in which case the output of this whole formula is just going to be the left-hand side. This AND gate is kind of canceling out the right-hand side. So it's just going to output G. So this thing actually does compute select FG. On the other hand, we want to show that this heuristic is useful. And the main idea here is to use something that I call reverse gate elimination. So what do I mean by that? Well, for any function G not equal to F, we have the following by gate elimination. If there's a size L of F plus 1 formula for the select function, then you can eliminate this extra bit we have here by setting it equal to 1, and then remove a leaf from the formula and get an optimal formula for F. Because this was of size L of F plus 1, and we removed one leaf, you get an optimal formula for F. Moreover, what that means is that you can go in the reverse direction. Any size L of F plus 1 formula for select F of G, F comma G, for any G not equal to F, can be obtained by taking some optimal formula for F and uneliminating a gate, that is, adding a gate to it. And the crucial thing here is that there's not too many ways to uneliminate a gate. And what that means is, if there were not too many optimal formulas for F, then there's not too many formulas of this form for the select function, which means there's not too many G that pass the test. And so that's kind of the intuition for why we have validity and usefulness for this baby heuristic. You have to do like one more trick if you want it to work with prefixes, but I won't have time to talk about this in this talk. And so that's the intuition that I'm giving for like kind of this main result. So the last thing I want to say is a little bit about this worst case algorithm. So I've already outlined our main result with this like bound in terms of the near optimal formulas. But what if you want a worst case algorithm that actually beats brute force? Well, kind of a natural approach if you had this algorithm is to split into cases. If the number of near optimal formula is large, then just try randomly guessing formulas and like maybe you'll hit one of them, hit an optimal one. On the other hand, if there's not too many of these, then you can actually use this algorithm and get some gains. And this thing works, but it only guarantees outputting a near optimal formula. In particular, if in the case where there's lots of near optimal formula, you might have a hard time. You only guaranteed finding a near optimal formula, not a strictly optimal formula. But using some ideas that I think are pretty neat, we're actually able to overcome this and get this worst case algorithm that beats brute force. All right, great. So thanks for listening. And if you have any questions, feel free to email me.